So thanks a lot for the invitation. Very happy to be here virtually today. Given the time difference, it's nice that I don't have to fly over there. Today I'm going to talk about the similarities and the differences between AI, deep learning in particular, and brains. So I'm going to start by telling you that AI could be a very good model for the brain, but then I will end by telling you that it's not a good enough model yet. So in this first part, this will be mainly based on two recently published papers where we reconstruct images, faces, or natural scenes from fMRI patterns using deep learning. And the second part here will be much more speculative. This will be based on this opinion piece that we recently submitted together with Ryota Kanai. So if you weren't living under a rock for the last 10 years, you probably all heard about the mounting excitement about AI and deep learning in particular. The most well-known deep neural network architecture, at least in computer vision, is the convolutional neural network that can be trained for image classification in a supervised way. So you show millions of images. Each time you give the network the desired output label, here, for example, a cat, and little by little, the network learns to tune its connection weights with backpropagation so that the next time around it will be more likely to assign the right label, even for images that it hasn't seen before. So you probably heard about networks like AlexNet, VGG, GoogleNet, ResNet, Inception, DenseNet, EfficientNet, all these networks that can reach very excellent performance in image recognition, even sometimes beyond human performance. And that's really I would say one of the areas where neural networks or deep learning have made the most widely known or the most widely publicized advances. But that's not all. And in fact, modern deep learning has a lot more to offer than these supervised convolutional networks. There are excellent methods for unsupervised learning where you don't need millions of labeled images. You just look at a data set and you figure it out for yourself. I'm thinking, for example, of GANS, Generative Adversarial Networks. And yet these methods are much less known, at least from the general public, than the convolutional neural networks. And that's a pity because, as you'll see, these models produce representations that have really fascinating properties. And I'll give you two examples of these representations that we also call latent spaces in unsupervised networks. First, in NLP, natural language processing, we'll talk about words or sentence embeddings. And then in computer vision, we'll talk about face processing and latent space for face representation. So first, in NLP, in natural language processing, you can use unsupervised training methods to create what is called a word embedding, which is basically an internal representation or a latent space. And this was done originally for words in 2013, the famous word-to-vec model. But the same principle is now routinely applied to sentences in current state-of-the-art models like BERT or GPT-3. So the latent embedding space is fairly low dimensional. For example, it can be 300 or 500 dimensions. Of course, that's a lot of dimensions, but I mean low dimensional with respect to the dimensionality of the inputs, when the vocabulary can be maybe 50,000 or 100,000 words, and the number of possible sentences is, of course, nearly infinite. So in this case, a word or a sentence is represented by a vector, and the vectors can be manipulated in an intuitive way with simple linear operations. And these operations make sense. For example, if you perform the vector operation queen minus woman, you sort of isolate the concept of royalty. And then you take this vector and you add it to the vector for man. And then the answer that you expect is exactly what you get, the word for king, right? And so that's an answer that makes sense to us. I'm going to show you a few more of these examples to drive the point home, just the same way that we defined the concept of royalty by subtracting queen minus woman. We can extract or isolate the concept of capital by subtracting Paris minus France. And then if we take this vector and we add it to the vectors for other countries like Italy or Japan, we get Rome or Tokyo. It makes sense. We can also extract more grammatical concepts like the difference between bigger and big. And if we apply this to different adjectives like cold or quick, we get the right answer, colder or quicker. If we now define our vector as a profession. So let's say scientist minus Einstein, and we apply this to different celebrities. Messi, you get midfielder. For Mozart, you get a violinist. Now, of course, this is a bit off. I might have said composer, but this is a fair mistake. And actually, this is something that a human might make, this sort of mistakes. You can also define X as a symbolic relation, the relation between an element, copper, and its symbol in the periodic table. And if you now apply this to other elements like zinc or gold, you get the correct symbol. And the final example is sort of the gastronomy example. If you take X as the difference between sushi and Japan, and you apply it to other countries, for Germany, you get bratwurst, and for USA, you get pizza. So I think all of this makes a lot of sense. You can think if a human has to do this sort of thing, these are basically the same associations or analogies that they would make. Now I want to give another example in computer vision. Of course, this is going to depend on what you train your system on, but let's take the example of a GAN that has been trained on a large data set of celebrity faces. I'm going to explain in a few slides how these GANs work, but for now, it's just important to understand some of their properties. So the latent space that we obtain here is of lower dimensionality than the input images. So it's about maybe 500, 1000 dimensions, even though the input image typically has maybe 100,000 pixels or 200,000 pixels. So in this latent space, as before, each point or vector corresponds to a face now, not a word, but a face. And because the model is generative, these GANs are generative models, then that means that you can take any vector in this latent space and you can generate the corresponding face and you can look at it. And so now you have all these vectors and you can start doing operations on them and you can look at the faces that are generated and you can ask if the results of these operations make sense or not. So we can play games like interpolation or extrapolation in this latent space. For example, let's try to interpolate between two faces. So we start with these 2 points in the latent space, and these are not real people. These are just arbitrary points, right? But as I said, we can always generate the corresponding image and we can look at it. So let's take a closer look at these faces, examine some of their differences. This one is turned to the left, this one to the right. The backgrounds are a bit different. This one is grayish, this one is redder. This one has eyes closed, this one open. He had dark hair and blonde hair. So now imagine that we're going to take a walk in this latent space between these 2 points. And every few steps along the way, we stop and we generate the corresponding image. So this is what you get. And the first thing to note is that every point along the way is a very valid face. So this would not be true if you were directly morphing in pixel space, then you would have very distorted or blurry images. But here, the morphing makes sense. So the hair color, for example, is gradually becoming lighter. The background is also slowly changing. The eyes are becoming more open. The face tilts to the right. The smile disappears, etc. Let's take another example, another point in this space. For example, this male face. So again, we can look at the differences between the 2 points. Obviously, one is male, the other female. But then there are also differences in hair length, the background color, the beard. You can interpolate, and boom, you see that the eyes gradually open, the hair gets shorter, the beard starts showing up, etc. So we can, of course, also interpolate between these 2 corners. And in fact, we can fill up the whole triangle by performing these interpolations. And every time, it always makes sense, right? We can also extrapolate, sort of expand outside of this compact region. You can imagine what this particular face would look like if we apply to it the same transformation as above. So you know that it should turn to the right, it should get lighter hair, it should get a redder background, a different hairstyle maybe, but it should keep the same gender because that's what happens at the top, right? And bam, it works exactly as you would expect. And just now, for the sake of completeness, we can fill up this whole rectangle. As the important point here is that every time you do this, sort of the result that you get intuitively makes sense to us, right? So in the previous examples, the vector that we were using tend to correspond to a transformation between 2 faces. And so they always differ in many ways simultaneously, like the haircut, the gender, the smile, etc. But sometimes you might just want to isolate one specific property, like the presence of a smile. And so if you want to do this, we can actually do it by having lots of faces. Then we can simply average over a lot of smiling faces. And then you average over a lot of neutral faces. And if you take the difference between them, then you can really isolate the smile vector, a little bit like we isolated the royalty vector in the words example. And so now you can add or subtract this vector from a given face, and you can see if the result of this vector operation makes sense, right? So here are 4 faces for original points in our latent space. What happens when we add the smile vector? Well, now each person is smiling more, but the identity has not changed. The features, the pose, etc., have not changed. So we can also remove 2 times the smile vector, and now all the faces are frowning. Right? We can perform other operations, of course, as long as we have the right vectors. For example, we can make the faces more male or female by adding a male vector, or more female by removing a whole lot of male vector. And so what you see here is that the latent space seems to understand that when things get more male, they should get a little stubble, but it doesn't change the other features like the haircut, for example. So these models, thanks to the structure of their latent space, they seem to have a pretty good understanding of what a face is in terms of the features and the relationship between these features. They know that there are things that change together and things that are more independent. For example, facial expression can be independent of identity, gender can be independent of hair length, etc. So again, it seems that this sort of latent space is representing visual information pretty much like humans would. And this brings us to our hypothesis, which is that all of this is so intuitive and it speaks to us. And maybe there's a reason for this. And maybe the reason is that our brains actually represent information in a very similar way, right? So that's the general framework that we're exploring. Now, of course, I need to make a clarification. We're not talking here about one specific version or a specific model or dimensionality or one particular type of GAN that would be like the human brain, because that wouldn't make sense. There's so many of these models and they all differ in subtle ways, but they're also all very similar. Why would one model be better than the other? Instead, my point is more about a whole class of models, which when they become powerful enough, would end up very similar to these high-level biological representations. And of course, there are differences between these models and the brain, and even between the models themselves, but they have a lot in common, and it's this common part that we assume is going to be like the human brain. So there are many things to test in this, and we have ongoing projects to probe this question from different angles. But for now, I'm going to focus on one specific angle, one specific way that we're testing this hypothesis, which is that if they are a good model of the brain, then they should allow for better brain decoding. So this is like a little teaser for what comes next. We're going to use the latent space of one of the generative networks to do brain decoding, hopefully better than what has been done before. So we showed subjects a bunch of faces like these in the scanner while we recorded the brain activity. And then we learned to map this brain activity onto the latent space of a GAN. And this way we could reconstruct an estimate of what face they were seeing. It's a little bit like mind reading. And in a more recent paper, we did exactly the same thing with another GAN that allowed us to reconstruct not just faces, but any natural scene that the subject was looking at. It's maybe less accurate, as you can see here, but it's still impressive considering that this is an entirely open-ended task with an infinite number of possibilities. So before I describe the exact network that we used and its latent space, I need to give you a little bit of a primer on unsupervised generative models for those who don't know. And I'm going to start with autoencoders. An autoencoder consists of an encoder network and a decoder network. The encoder learns to map an input image onto a lower dimensional latent representation, this code layer. And the decoder, we can also call it a generator, uses the code to produce a novel image. So during training, the network is trained to minimize the pixel-wise difference between the input and the generated images. So it needs to learn a useful way of compressing the image so as to maintain the essential features which are captured in this code or this latent space in the middle. So now this works fairly well in practice. There's a lot of compression systems that are actually based on this idea, but there's still a little problem here. As I said, the network is trying to minimize the pixel-wise difference between the input and the output, and this tends to encourage blurry images, as you can see in these samples. And it's easy to understand why. If you have a sharp edge in your image, like the contour of the face, if the edge is shifted by a few pixels to the left or to the right, perceptually, it doesn't bother a human observer, but for this type of network, it's going to generate a large error signal. And so the best way to avoid this is by blurring the images, because then you'll have a lot of small errors, but you don't have any large ones, right? So what we would want instead of this pixel loss is a loss that is perceptual rather than just pixel-based. And so this perceptual loss could be implemented as a separate neural network, and that's actually the basic principle of GANS, Generative Adversarial Networks, right? So in fact, GANS are slightly more complicated than this, and it's really a whole separate class of models. But for the sake of simplicity, let's assume now that in addition to our generator, which turns the latent codes into images, we also now have a discriminator network, which looks at the images and tries to guess if they were made by the generator or if they come from the original data set. So this discriminator is itself a deep neural network like the generator, and they are both trained together with backpropagation, and the training is called adversarial because they have opposite objective functions. Basically, your discriminator is rewarded whenever it is right. So when it is able to look at the generated faces and tell, even sometimes using very subtle differences, and tell that they are generated and they don't come from the original data set. But your generator is going to be rewarded when the discriminator is wrong, right? So it's really the exact opposite function. That means that the generator has to be able to produce faces that are good enough that the discriminator is fooled to believe that it belongs to the original data set, right? And it's easy to see that as training progresses, when you have a really good discriminator, then the generator does not have a choice. It has to produce really, really good faces so that it can still continue to fool this discriminator. And that way, we can really generate faces that are much, much better than with other methods, right? So for example, with this GAN technique compared to a standard autoencoder, or in this case, this is a variational autoencoder, but it's the same principle. You can get much clearer reconstructed images with a GAN with much sharper edges. Even though these images are still kind of a bit, let's say, unnatural, but this is an old GAN by the standards of the field, right? This is 2016, and it's a very young and fast-moving field. You can see that clearly in this Twitter post from Ian Goodfellow. You can see in the space of 5 years how much progress these GANs have made really on face generation specifically. And now you have to remember that all of these are not real people. These are all fake faces. Maybe in 2015 it was easy to see, but nowadays it becomes really difficult to not see these as people. Like this woman here, I really can't help but imagine her as a school teacher somewhere in South America. But in fact, these are all just points in a latent space, right? That's quite remarkable. And if you're interested in this, I invite all of you to explore this website, thispersondoesnotexist.com, where you can create an infinite number of faces just like this, just by clicking on a button. So the work that I'm going to present now, we started doing it in 2016. And so unfortunately, the faces that we used in our experiments and that we're going to reconstruct from fMRI, they're not of the highest possible quality. If you redid the experiment today, you could hope for much nicer reconstructions, but it is, this is how it is. So in our study, we kind of used the best of both worlds. We used an autoencoder, so actually a specific version called a variational autoencoder, so VAE, and it was coupled with a GAN, with the generator and the discriminator. And so the result is a so-called VAE-GAN network. And we got the algorithm from this paper, so we didn't invent it, but we implemented it and we trained it ourselves on this large celebrity data set of 200,000 images. So the VAE-GAN network consists of the autoencoder that encodes a face into a 1024-dimensional latent space. And then the generator here converts these latent codes into reconstructed images. And during training, we also have a discriminator network that helps us to produce this latent space of efficient dimensions, as I was just showing in the previous slide. So after training, though, you can freeze the weights of this part of the network, so we don't touch it anymore, and the discriminator is dropped. We don't need it anymore. We just need the encoder to go from an image code, to a code, and more importantly, we need the generator to go from the code to an image, because that's how we're going to reconstruct the faces from the brain patterns. And so this is actually the network that I used a few slides ago to demonstrate all these vector operations. So we know we're working with a pretty good latent space because the vector operations make sense in this space. Okay, so finally, in addition to the VAE-GAN model, we also had a baseline model for comparison. This is based on PCA, Principal Component Analysis, of the celebrity data set. So it's like a little bit like version 0 of unsupervised generative modeling. We retained the first 1024 principal components as our latent space representation here. So that's a fair comparison because we have the same number of dimensions. And just like before, we can encode faces into this latent space with PCA decomposition, and we can decode the latent vectors into faces with a simple inverse PCA transform. But this was actually the state of the art back in 2016. So this is what we did. We presented a bunch of faces to human subjects, and then we created a mapping from the brain representations to the VAE-GAN or the PCA latent space. And once we are in the latent space, we can just use the generator networks to reconstruct the faces that you're seeing here. So as you can see, the PCA is actually fairly good, but VAE-GAN appears to be quite a bit cleaner. So for this study, we presented 4 subjects with about 8,000 faces each, and this amounted to 16 hours of scanning per subject. And of course, they didn't do this in one sitting. This was split across 8 or 12 different sessions. And because this data is very expensive to collect, we're very happy to share it for free on the Open Neural platform. So you can go and download it if you want. So how do we get the mapping from the brain space to the latent space? There are 2 steps, both with a general linear model, GLM. In step 1, we take all our 8,000 training images and we encode them in the latent space, shown here in red, and we learn a linear transformation matrix W that predicts how each voxel is going to react to these latent dimensions from the model. In practice, if Y here is the response of the brain to the 8,000 faces, we can assume that it can be modeled as a linear transformation W of the latent variables X in this 1024 dimensional space, right? So for the training step, we have X, we have the images or their latent representations. We have Y, that's the brain responses, and we simply solve this system for W. So we do a little bit of linear algebra. I don't need to go into the details unless anyone has a question about this, but that's how we get our matrix W that we're going to use in step 2. I just want to say one word here about the underlying assumption. Of course, this type of linear model is trivial, and we can probably do much better if we use a more fancy model, but this is voluntary here. You remember our hypothesis is that this latent space is a good model for how the brain represents information. And if that's true, then a simple linear transformation should be sufficient. Of course, if we had a very fancy brain encoding model, you might be able to predict brain activity even directly from the pixels, right? But then you wouldn't really know much about brain representations in that case, right? In our case, if it works, it will mean that this latent space is not far. It's actually one linear transformation away from how the brain actually represents data. Okay, so in the second step, in the test phase, we want to turn things around. Instead of going from the latent space to brain activity, we want to take a brain activation pattern and we want to turn it into a latent vector and eventually into a face. So we do this for new images that were not used in training the brain decoder. We have only 20 of these test images, but each of them was seen 45 times. So we have a pretty clean brain response patterns for each image. So starting from the same equation, we now have Y, the brain response, we have W, the matrix that we learned in step 1. And so what we want now is to extract X, the representation of the face in the latent space. And again, for this, we're just going to do a little bit of linear algebra. And so that's how we get X. And once we have this latent vector, we can then pass that vector through the generator and we obtain the reconstructed face. So here are some examples of face reconstructions from each subject. The leftmost column each time corresponds to the original faces that the subject actually saw. The middle column here corresponds to the face reconstruction from the VAE-GAN model. And the third column shows the reconstructions from the PCA model. Here is the second subject. And so I hope you can see that the VAE-GAN reconstructions are just typically better. Not only they're more visually pleasing, but they also capture more features of the faces. For example, the glasses here are nearly absent for PCA, but they're quite visible for the VAE-GAN model. These are examples from the 2 other subjects. So I'm just going to let you explore a little bit. So then we can ask which brain voxels contribute to this brain decoding. Actually, I didn't have time to go into the details, but we didn't use all the voxels in the brain for these face reconstructions. We selected the most informative voxels. And of course, we did this selection based on the training set alone. So there's never any what we call double dipping. We never peak at the test set during training. And so the selected voxels that you can see here included a very distributed representation in occipital, temporal regions, in parietal also, and a bit in frontal regions. And the color bar that you see here corresponds to the number of subjects that shared each of the voxels in their selection. So as you can see, there was really some general agreement between the 4 subjects. And so we can also ask which brain regions contribute more to the face reconstruction itself. And so what we did is for each subject, we divided our voxel selection into 3 equally sized subsets. So we have an occipital subset, basically everything behind this blue plane. We have a temporal subset, everything below the red plane, and the frontal parietal region, everything above the red plane, right? So these are not really functionally defined areas. These are not your standard regions of interest. But the reason we do it this way is that at least here the comparison is fair, because each of the 3 regions has the exact same number of voxels, and we know that the quality of the reconstructions is strongly dependent on the number of voxels. So what we did then is we performed our face reconstructions, but with the 3 subsets separately, and then we measured reconstruction performance with what we call a pairwise decoding accuracy here. So chance level is at 50%. And we found that it was mostly the occipital and the temporal regions that contributed to face reconstruction. The frontal parietal region was actually not significantly above chance, right? And each time you can see that the VAE-GAN model is always better than the PCA model. So now I want to show you that our transformation matrix W is really like a treasure trove for exploring face representations in the brain. And that's because what this matrix captures is for each voxel in the brain, it tells us what is the preferred latent vector that tends to maximally activate this voxel. And so if we care about a certain face property, like gender, for example, and if we have a corresponding latent vector, you remember I showed you a few slides ago how we can compute this male-female vector. So then what we can do is we can compare this vector against the preferred vector for each voxel in the brain, and then we can make a map to find out where gender information is encoded in the brain. And that's what you see here. So you see that this type of information is fairly distributed across occipital and temporal regions. But for example, it strongly emphasizes the FFA, the fusiform face area, exactly as you might expect if you're a neuroscientist working on these questions. So now, of course, all this here is not limited to gender. Without redoing any experiment, we could ask similar questions about other features, about race, for example, or age, smile, etc. So that's what I mean by a treasure trove. There's really a lot to explore still with this matrix W. Okay, the final thing I want to talk about is that we also tried to decode what face a subject was imagining, not seeing, but this is really a type of mind reading task, if you want. So this problem of mental imagery decoding has been addressed before, but may need to distinguish category level information. For example, is the subject thinking about the face or about a house? And I hope you can understand that it's much more difficult to do this at the level of individual exemplars because we know it's a face, but we're asking which face is the subject thinking of, right? So to test this, what we did is we asked each subject before the start of the experiment to choose one face among 20 possibilities. And then they were asked to imagine this particular face in the fMRI scanner without anything on the screen. And then we can use our brain decoder, we can use our matrix W to estimate the corresponding latent space vector. And as before, we calculated the classification accuracy, which we found to be around 85% correct, which is pretty good, but only in temporal regions. It was a chance in the other regions. And so this probably reflects the strong involvement of these temporal brain regions in phase processing or in high-level phase processing. So that means that if we decode the latent vector of the imagined face and we compare it to the latent vectors for the 20 possible faces, most of the time we're going to pick the right vector. And so this is one example subject for which the true imagined face, this one, was the most similar to our decoded vector. So rank 1 among all the ranked faces. And now, of course, you don't just want to know the rank. I guess you want to know what the face looks like when we reconstruct it. And that's admittedly a bit disappointing, right? The subject was imagining this, but we're actually reconstructing that. But you can still recognize some aspects. And I would say it's pretty good given that our reconstruction system was trained with visible faces always, right? Never with imagined ones. So going back to the initial hypothesis, at least for faces, the DNN latent spaces appear to be a pretty good model. So we can check this box here. Of course, does it prove the hypothesis? Not yet. There's a lot to explore still. One thing that we wanted to do initially was to look at words and sentences. We wanted to compare the brain representations to word or sentence embedding models like Word2Vec, GPT-2, or BERT. But in the meantime, there's already been a couple of papers that were published exactly on this with very solid data. So we actually don't have to do it. We can just check this box and thank these people. And so we decided instead to explore another domain beyond faces. We asked, can we reconstruct any image or scene? So for that, we would need a powerful GAN model, a GAN that could reconstruct all visual scenes, right? In 2016, when we started these experiments, the best state-of-the-art GANs were good for constrained data sets like faces, but they were not good for broader, unconstrained, open-ended data sets like, for example, ImageNet, where there's 1,000 different categories, right? But actually now they are. For example, a couple of years ago, DeepMind released this BigBiGAN network, which is pretty much the same, but for all of ImageNet. So it can generate any object category. For example, it generates lots of dogs because ImageNet is very biased towards dog categories, but it can also generate sharks or birds. And in fact, these animals here do not exist. They look like realistic natural images, but they all just points in this BigBiGAN latent space. And so this means that we can do the same kind of stuff as before. We can, for example, interpolate across categories, and that's what you can see here. So if you ever wanted to know what's halfway between a shark and a dog, well, that's your answer here in the middle. I don't know what this is, something like an octopus or a calamari. I don't know. But for us, this really opened up a whole new avenue of testing and comparing with fMRI. So we did exactly the same thing as before, but now instead of mapping brain data to our VAE-GAN latent space, we map to a BigBiGAN, or actually this is another variant called BigBiGAN, but we don't need to worry about this. And so based on this, we can reconstruct rough estimates of what the subjects are seeing. It's not perfect, but it's much better, for example, than a PCA with the same number of dimensions. So we didn't do this with our own data, by the way. We used an open source data set from OpenNeuro, which was published by Horikawa and Kamitani, with 5 subjects and 1,200 images for each subject. So let me show you some reconstructions. The original image is always here on the left. Next, I also show the direct reconstructions from this BigBiGAN model. So this is not brain reconstruction, right? This is just a model reconstruction. We can consider this as the noise ceiling if you want. That's how good we would be if we had a perfect estimate of the latent vector. And of course, you can see that it's not perfect already. So with our model, we cannot hope to do any better than this, right? So here are the reconstructions from the 5 different subjects that we're seeing all these same images. You can see that the reconstructions always differ between subjects and also compared to the original, but there's also lots of similarity here. You can sort of see the logic. It's really far from random, and in some cases, it's even fairly accurate. Some more examples. In the last one here, of course, the BigBiGAN itself got it wrong. It thinks it's a dog, even though it was a leopard. So there's really no hope for us to get it right, even if we get the correct latent vector. Now, if we compare our method to the previous state of the art, so these are the 4 columns here on the right, we can see that there are many models that are sort of more faithful to the original in terms of the pixels, right? So for example, this Ren et al. Model is pretty good, but there's never, in most cases at least, there's not an identifiable object in the picture, whereas in our case, there's always an object. It's often the wrong object, but at least I would argue that it's a better guess, or it's a nice try. Okay, so to complete the table, I think we can check this box as well. The BigBiGAN latent space seems to be a fairly good model for human brain representations. At least we can use it to decode these brain activity patterns. And I'm not even talking here about that study that came out just last week. I don't know if you guys seen this. This is remarkable. They found these multimodal neurons in the latent space of certain deep neural networks. Like this neuron here, this is an estimate or a visualization of its preferred stimulus. This was a neuron that responded to any picture of Donald Trump from any angle, but also to the written words, Donald Trump. And that's very similar to the famous Halle Berry neuron that was found in the human brain in 2005. So I think we can safely say that there is at least some truth to our hypothesis that these latent spaces are fairly good models of brain representations. Now in the final part, I want to take a step back and try to now consider the entire brain. So the current AI architectures that we were talking about before, they might be good at explaining vision or face perception or language or maybe decisions, but the human brain, of course, is probably more than the sum of these parts, right? And so this type of domain-specific approach is unlikely to result, I would say, in true artificial intelligence. And what is missing, I would argue, is a way to put it all together, to combine these different parts in a meaningful way. And there is a theory in cognitive science about how this could be done. And actually, this is one of the major theories of consciousness today. That's the global workspace theory, which was introduced by Bernard Bars in 1993. So according to this global workspace theory, the brain is divided into specialized modules for specific functions, like these white and gray nodes here, with long distance connections between them going through the center here. And so under certain conditions, for example, if this is warranted by the inputs or by the task requirements with the process of attentional selection, the contents of 1 or 2 specialized modules illustrated here in red, the contents can be broadcast and shared among the distinct modules. And it is this shared information at each moment in time, the global workspace here in the middle in red, it is this which constitutes our conscious awareness, according, of course, to this theory. So now in this context, it's a bit like each of the current AI models I was describing before for image classification, face recognition, language models, etc. Each of them is like one branch on this graph, what they call a modular processor. But what we're missing is, I would say, the most important, the integration and broadcast here in the middle. So could we imagine a deep learning implementation of the global workspace theory? This is actually what we've been working on recently, together with Ryota Kanai at Raya here in Tokyo. And we just published last month, I think Ryota is in the audience, right? And so we just published last month a revised version of our opinion paper, Deep Learning and the Global Workspace Theory, that I'm going to describe now. Now, I just want to warn you and maybe disappoint you a little bit. This is very much work in progress, and so I will present the general framework, but there's going to be no actual results at the end, so I apologize in advance. So what we envision is something fairly similar to this global workspace picture with the concentric circles that I was showing you before, but now with deep learning components everywhere, right? So we could have a bunch of pre-trained models for a range of different functions, domains, modalities, etc., similar to the ones we were discussing before, like image classification, face recognition, maybe language models, anything you want, really. And this list here, by the way, is neither limitative nor exhaustive. It's just an illustration. But what we want is somehow to connect the latent space of all these guys together using this central shared workspace, which we call the global latent workspace, so GLW for short. And so for this, you might realize that the main challenge is to somehow be able to transform latent representations from one domain into another representation that the other systems can understand. That's what all these red arrows here represent. And this is in fact a problem of neural translation. For example, we need to be able to translate visual object features into word embeddings or into speech features. But this is not a simple translation problem because in most cases, we cannot rely on matched data sets. For example, we don't necessarily have a data set for all the motor affordances that are allowed by English speech sounds. So that's why this translation has to be unsupervised. So is it possible to learn to translate without having access to matched data sets? But this is a question that was actually addressed many times recently in NLP, and the answer is definitely yes. And the reason is that all of these languages, French, Japanese, English, all these languages are grounded into a common reality. We all live in the same world. And so their latent spaces have to share a similar topography. That means that if two words are close together in one language, for example, chien and chat in French, that means dog and cat, then they should also be close together in the latent space of another language here in Japanese, right? And if that's true, then we should be able to align the space without directly matching data. We don't need to be told explicitly that this is the Japanese word for chien. We can figure it out by just looking at the global structure here of the two spaces and trying to fit them optimally as shown here on the right. So based on this principle, the global workspace should also be able to align multiple input domains or multiple modalities, even if there's no ground truth for this alignment. So to do this in practice, just like most of these unsupervised neural translation systems, we propose to rely on what we call cycle consistency as the secret sauce. And it's actually very simple to understand. The principle is that when you translate from A to B, and then you go back from B to A, well, you should end up not far from where you started, right? So we can do this. We can check how far we land, and we can optimize the whole system to minimize this distance, or in other words, to maximize the cycle consistency. And this is not something that's limited only to language. You can actually also do this in other domains. So for example, this is the principle behind the cycle GAN. That's a system for image-to-image translation. And the system can learn to align, for example, representations of zebras with horses without having any matched images. Then what you can do is you can feed an image of zebras and you can turn it into regular horses, or you can zebrify. I know it's not a word, but I like it. You can zebrify any horse picture, or you can learn to translate summer into winter landscapes and vice versa, or Monet paintings into high resolution photographs or vice versa. So this is what we want to use behind each of these red arrows in our global workspace system. And then once we've learned to translate with this cycle consistency trick, then in practice, how would it work? How would this give rise to enhanced functionality? So let's try to follow the operation of the workspace in a standard scenario, much simplified, of course. In this illustration here, the workspace is going to be in blue. here in the middle, and there are 4 modules connected to it, or potentially connected to it. There's a task module here at the top. And for now, let's say that the task is defined at the beginning. The task is defined as walk in the jungle, right? So we have a language module, we have a movement module, and a vision module. And based on the task, the initial task here, the system might decide that maybe vision is relevant. You want to keep your eyes open. And so that's why vision gets connected to the workspace here. And that's represented by these solid red lines, right? So solid red for the connected modules, and a dashed line for the disconnected modules. So connected here means that the latent space of this module is somehow clamped to an internal copy inside the workspace. So if something changes in the world, then the workspace will know immediately. And if something changes in the workspace, then this module will also receive the updated information. So it's bidirectional. So now, step 1, as you start walking in the jungle, suddenly a tiger appears in your visual field, right? And because the vision module is connected, immediately this information will get translated into a representation that's suitable for all the other modules, even those that are not currently connected, right? So that's the broadcast operation happening right here, right? So this translation here, for example, from vision to language, this might reflect the concept of semantic grounding. That's the linguistic information about tigers that pops in your head as soon as you see a tiger, right? And this connection here, this one, this translation reflects what I would call the motor affordance. That's the sudden urge to flee when you see a tiger, for example. But you don't have to do it just yet, right? But based on all this information, the attention system, which is not represented here, but it's very much part of our workspace idea, the attention system would decide, wisely, I would say, to connect the movement module to the GLW. That's what you see here. And bam, an escape response is going to be produced. But in this case, no language output is recorded. You don't have anything to say, you just run away. But now we can imagine also a slightly different scenario in which the task would have been different. For example, now you're just visiting a zoo. And in that case, for the same tiger visual input, your ultimate decision might be instead to connect the language module instead of the movement one. And then you're going to say, oh, look at the pretty tiger, and you don't actually escape, right? So this is one way that we could coordinate information from different neural networks and use it in a flexible way to control the inputs and outputs of other neural networks. And ultimately, I think this would be a much more complete model of the entire brain. So to conclude, I would say what is nice about our proposal, the GLW, is that it works strictly with currently available deep learning ingredients, right? So we have these domain-specific modules that are just pre-trained neural networks for a variety of tasks. And there are literally thousands to choose from. There's so many pre-trained models now in the literature. So these would correspond to the gray subnetworks in this picture. Then we have an attention system to select, as shown here, to select which subnetworks get connected to the workspace here in red. And that can be done with the transformer architecture, which is very popular these days. And finally, we also have our secret sauce, the unsupervised neural translation, trained with cycle consistency. And that can serve the role of broadcasting information inside the workspace, shown here in red. So all the ingredients are here. Now, all we have to do is implement. And we're working on it. But as I warned you at the beginning, I don't have any results to show on this yet. We're not the only ones working on this. And in fact, in particular, there's a very recent, I would say, competing implementation that was published less than 2 weeks ago by the group of Yoshua Bengio and Anirudh Goyal. It's really the same spirit, but there are key differences. When we want to take advantage of pre-trained modules, they propose to train the entire system end-to-end jointly. So for them, this tends to alleviate this problem of unsupervised neural translation because all their modules can jointly learn to speak a common language. And so they can do all the communication with just transformer attention mechanisms like we propose. So this is a very nice and elegant implementation, but I would say maybe possibly less flexible than the one we propose because they cannot make use of all these very efficient pre-trained models. And of course, you'll have to stay tuned to see which model works better. But I just would end by saying that this is a very exciting time to be working on these questions. And I will end on this, and I will take questions in case there are any.